here are the assumptions. The vector field, capital F, is a gradient field, del F. And remember, in component form, you can think of a gradient field as a vector of partial derivatives, f sub x, f sub y, f sub z, where the function f of x, y, z is what's called a potential function. Okay. This vector field is continuous, which means its components are continuous on a simply connected region R, and C is piecewise smooth in R. Okay, what is a simply connected region R? And it's actually an open region too. So if you want to picture a simply connected region, at least in the plane, it's easy to do. If R happens to be in the plane, then a simply connected region looks like, can look like this anyway. Doesn't include its border if it's open. So I make the border dotted, and there's no holes, there's no separations in it. If that's the case, then it is a simply connected region. Okay. So here's the big note of the day, which is going to turn out to be the fundamental theorem of line integrals. So suppose we want to evaluate the line integral with respect to the vector field, f dot dr. Then the assumption is f is a gradient field, so you can replace the vector f notation with the del f notation. They're one and the same. And then if we go to differential form like we did the other night, you can think of del f as a vector full of the partial derivatives of f. You could think of dr as a vector of differentials, which is a little bit of abusive notation because it's not a true vector, but the notation works. And if you go ahead and take this dot product, you do get the differential form, the integral over c of f sub x dx plus f sub y dy plus f sub z dz. And it's been a while. You may or may not remember that this is the total differential of f. And we call it df, or you're used to calling it dz a couple of chapters ago, right? So if we play with the notation then, we could call this the integral over c df. And if we parameterize c in terms of a vector valued function with a parameter like t, then there's no reason why we couldn't write this integral as the integral from t equals a to t equals b df dt if you multiply and divide by dt. Of course, there's a lot more going on there, but we know that differentials behave like algebraic quantities. And then if you think about this is like turning your line integral, you're parameterizing your line integral and turning it into an integral with respect to t, a calculus 1 type integral. So how do we take the integral of df dt with respect to t? Well, we actually know how to do that, don't we? That's just f, isn't it? Now, evaluated from a to b. Now it's important to realize that this f, this function f, is a function of 3 variables. So it's when you integrate this is the regular fundamental theorem of calculus from calculus 1. When you integrate this, you get f of, okay, it has 3 variables, x, y, and z, but they're all in terms of t, so it's ultimately a 1 variable function when you parameterize it on that curve, c. And you integrate df dt with respect to t, you do get f of x, y, z, all with respect to t, evaluated from t equals a to t equals b. That's the fundamental theorem of calculus from calculus 1, isn't it? So what does this turn out to be? Well, remember you input the upper limit first, so that becomes f of x of b, y of b, z of b. So f evaluated at b minus f evaluated at the lower limit, a. So that's f of x of a, y of a, and z of a. This is if f is has 3 inputs. If it only has 2 inputs, then you delete the third coordinate there. And that's an interesting result, isn't it? Maybe it may not, the full appreciation of this may not be evident to you. But what we're saying is if you want to evaluate a line integral, remember what, let's go way up to the beginning, and let me expand the view here. Let's zoom out so we can see this whole thing. One more time. Let's make it 65%. There. Now you can see this whole thing. What we've just done is we've gone from the line integral with over C with respect to the vector field f. We've gone to a formula for evaluating that, which just involves the potential function for f. And what we're saying then is, hey, if you want to evaluate this line integral, you don't have to use those special formulas from the last section. You don't have to use that at all. You don't have to use f dotted with r prime of t dt. You don't have to integral that. You don't have to use that. You can just take f of the endpoint, which, f of essentially b minus f of essentially a. F evaluated at b minus f evaluated at a. Doesn't that look familiar? Yeah, it's essentially, it really is the fundamental theorem of calculus, line integral version. So what this is saying is to evaluate this thing, you can take f of the endpoint minus f of the beginning point. What do I mean by that? Well, remember what we're doing. This is a line integral. A line integral with respect to a vector field. So we have, say, a curve, C. Maybe it's parameterized like that. Maybe we're going from this point to this point. This point would be maybe given by, if C is represented by a vector valued function r of t, then this beginning point might be r of a, and this end point might be r of b. But remember, r of b is just x of b, y of b, z of b. And r of a is just x of a, y of a, z of a. So what we're saying here is pretty trippy if you think about it. We're saying we can evaluate this line integral over C, not worry about what happens in between the beginning point r of a and the ending point r of b. It doesn't matter. This integral is independent of path. So no matter what C looks like, if it looks like that, if C looked like this instead, or maybe it's a straight line, doesn't matter. You're going to get the same value if the vector field f is conservative, if it has a potential function, which we represent by lowercase f. Let's suppose our vector field f is a gradient field, del f, where the potential function f of x, y, z is equal to negative the opposite of 1 over x squared plus y squared plus z squared. Find the work done, so I suppose f is a force field also. Find the work done in moving a particle along a smooth curve C, joining the beginning point 1, 0, 0 and the ending point 0, 0, 2. So if you've absorbed anything, then you're realizing, since we're given the potential function, this is a super easy problem compared to what we did last time. All we have to do is plug in the endpoint into f for x, y, and z, plug in the beginning point, subtract, and we're done. That's huge. So because what is work? The work is the line integral, right? Work is the line integral over C, whatever C is, of f dot dr, right? That is work here. the work done by the vector field. We weren't even told what C is. We're just told it's a smooth curve. Well, that means we can apply FTLI. So this equal sign is by the fundamental theorem of line integrals, which is the statement we just got done talking about. This statement up here, which I forgot to circle, this is essentially the fundamental theorem of line integrals. Okay. So all we have to do then is, okay, here's our f up here. Let's take f of the endpoint. What's the endpoint? So we take f of the endpoint minus f of the beginning point. What's the endpoint? So f of 0, 0, 2 minus f of the beginning point, 1, 0, 0. And if you plug in 0, 0, 2 in here, the only thing that doesn't zero out is the 0 squared plus 0 squared plus 2 squared, right? The opposite of 1 over 0 squared plus 0 squared plus 2 squared. So that's what? Negative 1/4? So I'm plugging in 0 for x, 0 for y, 2 for z. Everybody see where that's coming from? And then minus f of 1, 0, 0. Okay, it's negative to begin with, so that would be minus 1 over, okay, now we're plugging in 1 for x, so it's 1 squared plus 0 squared plus 0 squared, showing you a little more detail in that one. And so you get negative 1/4 plus 1 minus a minus 1, which is what? 3/4.